Earlier, we looked at geometric series. That was all about finding the sum of the first n terms in a geometric sequence. But now, if we talk about infinite geometric series, what we're really concerned with then is S of infinity. In other words, we want the sum of all of the terms, infinite number of terms. That's what this is. This is the sum of all terms in a geometric sequence. Now you can't always find this, but this is the concept, this is the idea. The idea is to try to find the sum of all of them here. So before we had an equation, before we had an equation that went like this, S of n, this is for a geometric series. It was S of n equals u1 times 1 minus r to the n, all that over 1 minus r. So the idea is, don't make n just n, make it infinity, and then see what happens. So this is not really so simple to look at. Whoops. So what we're going to do then is talk about the concept of convergence and divergence. And I think that may help to sort of explain why we can sometimes do it and why we sometimes can't. So an example of something that's divergence. Let's maybe just do an example here. So let's do a geometric sequence. Let's do one that goes, let's say it doubles every time. So 1, 2, 4, then it goes 8, then 16. It keeps doubling. So the next one is 32, 64, so on, so on. If we try to do a graph of n, so here as we just get n very, very large, this is the idea here. As n gets really, really large, well, let's look at what the sum of the first n values would be. Well, if I have a lot, let's say n is some small value, then the sum is some small value. And if I make n larger, then the sum is larger. And in fact, it gets larger faster. It's what we call exponential. So something goes like this. So the problem is this. When we say it diverges, we mean it does not, like Sn here, does not reach some equilibrium value here. So what I mean by that here is that we could say this thing right here, it diverges. In other words, it does not, we could say Sn, that's the key thing. Sn does not reach some value as n approaches infinity. As we get larger and larger n values, Sn just gets larger and larger as well. So because of that, we cannot calculate S infinity, because we could say that this sum diverges. In other words, we can't find what value it is, because as you get an infinite number of n, the sum is also infinite. It's infinitely large. As you get larger, it just gets larger. So the question is, how big do you want to go is how big you go. So that's not very nice. So divergence isn't very helpful for us. But what about if things are converging? So we say convergence. What is that? Well, I'll give you an example of something that does converge. Maybe we take this and take it the opposite. Maybe we go 4, 2, 1. So here we're going to divide by 2 each time. And keep going. So 1 divided by 2 is 1/2. That divided by 2 is 1/4. That divided by 2 is 1/8. That divided by 2 is 1/16. And so on. Now let's look at a graph of n versus the sum of all the n values. Well, at first, if we did, like a small value, of course, it would change a lot. But as we keep going, do you notice here we're adding smaller and smaller values? Which means if we made n really, really big, do you see we'd be adding pretty much nothing? In other words, as long as you figured out the first bunch here, you pretty much have the answer. In fact, that's something that converges. In other words, maybe it looks something like this. So here, do you see how this is an asymptote here? This means this graph gets infinitely close to some value here. So here in this case, then, we're going to say Sn does reach some value as n approaches infinity. Therefore, we can calculate. We can actually figure out what happens when you add up all the terms. You add up an infinite number of terms. So there we can calculate S of infinity here. And the way we actually do it, we have an equation. It turns out the original equation that we looked at for a geometric series, it actually becomes this. So this is the infinite geometric series. Here's the equation for it. Remember, series means sum of all the terms. So it goes like this. S infinity. And it's really, really simple. It turns out it's just u1 over 1 minus r. That's the equation. Okay, that's it. But there's something really important. Well, first of all, this tells us this is a sum of the first infinite number of terms. Remember, u1, that's just the first term. Remember that r is just a common ratio. That's the number you have to multiply everything by. So that's the common ratio. But there is a really important sort of thing that has to happen, though. Okay, I'm going to put lots of stars by it because it's super important. The absolute value of r must be less than 1. This only works if this is the case. So this means absolute value of r is less than 1. In other words, if r is 0.5, is that less than 1? Yes. But absolute value just means it's allowed to be a negative. So for example, what if r is negative 0.3? Well, absolute value just makes a negative positive, so that would be just 0.3. Is that less than 1? Yes. But what if r is, let's say, negative 4? Absolute value of that is positive 4. Is 4 less than 1? No. How about r is 5? Well, that's also not less than 1. So just showing you examples. In other words, really, the value must be between 0 and 1, effectively, but negative or positive. So this is how we use this. So now let's do an example with this. It actually looks really easy, but the key thing is to check that the absolute value of r is less than 1. So let's do this example here. This is going to be a two-part example. We're going to sort of do two parts here. So first, write 0.3 repeating as an infinite geometric series. So first we're just going to write it out as sort of just one thing plus another one plus another one. So in this case, let's actually do it. Well, 0.3, what that means is that's 0.33333 keeps going forever. So how can I write that? Well, that's like saying 0.3 plus 0.03 plus 0.003 plus... See, now I've got a series here. But I just need to write this maybe in a little bit nicer form. Maybe I'll write this as a fraction. And 0.3, that's just equal to 3 over 10. So I can say that's equal to 3 over 10 plus, and this is just 3 over 100. And this is just 3 over 1,000, and so on. So that's it. That's all we needed to do for this. This is really easy. It's just equal to this. Now what you can do then is go one step further, which is the second part here. Find the sum of this. So it turns out this was the same thing, right? 0.3 repeating was equal to this. 3 over 10 plus 3 over 100 plus 3 over 1,000 plus 3 over, you can keep going. But I don't feel like keeping going though. So if we want to find this sum, in other words, we want to convert this to a fraction, hopefully. We're going to see what we really get. Now, if you know about this, you know it's 1/3, or you can do this on your calculator, put in 0.333333, put in lots and lots and lots of 3's, and ask your calculator to then convert it to a decimal. But you have to do enough 3's, though. If I just do a few of them, and I just convert that to a fraction, it doesn't work. You have to do a lot more 3's before it works. But I want to show you how to do it in general, because you can do it for any complicated case. It works like this. So using this simple example, we can still see how to use an infinite geometric series. So this is 3 over 10 plus 3 over 100 plus 3 over 1,000 plus ... I think the first thing to do is actually check if it is, well, first of all, if it's geometric. And let's see if it really is. If it's geometric, that means, well, we know that u1 is equal to 3 over 10. That's the first term. And we need to figure out r. How do we figure that out? Well, we can do 3 over 100, that's the second term, divided by the first term, 3 over 10. What does that give me? Well, dividing a fraction by a fraction is the same thing as multiplying by the reciprocal of the bottom. So in other words, this. If I do that, the 3's cancel out, so I get 10 over 100. So that gives me just 1 over 10. That reduces. All right, let's try this one. 3 over 1,000 divided by 3 over 100. Again, I divide by the, multiply by the reciprocal. So 100 over 3. The 3's cancel out. 100 over 1,000 reduces again to 1 over 10. Therefore, my common ratio is 1 over 10. That's all I have to do here. So my u1 is this, my r is this. In order to do the infinite geometric series, I have to double check though that the absolute value of r is less than 1. So is the absolute value of r less than 1? Let's see. Well, r is 1/10, and 1/10 is indeed less than 1. So yes, that means I can do it. Therefore, I'm in business. I just go s infinity equals, well, it goes u1 over 1 minus r. That was the equation. So it's really easy. Then it's just u1, which is 3 over 10, divided by 1 minus r, which is 1 over 10. Now all you have to do is just convert this and simplify it a little bit. So let's leave it as 3 over 10 divided by, and I'm going to make this a common denominator. 1 is the same thing as 10 over 10 minus 1 over 10. I do that because I want to deal with the bottom here. So it's 3 over 10 divided by 10 over 10 minus 1 over 10 is 9 over 10. Oops, I guess I need a little bit more space here. 9 over 10. And dividing a fraction by a fraction is the same thing as multiplying by the reciprocal. So that's 10 over 9. The 10's cancel out, so I have 3 over 9. Well, that reduces. I can divide them both by 3. 3 over 3 is 1. 9 over 3 is 3. Therefore, it is 1/3. And that should be obvious, because if you did 0.333, and let's just say you had a whole bunch of 3's. You have to have lots and lots and lots and lots and lots and lots of them. If I do that many 3's, let's just say until my calculator stops thinking about it, I can say enter, and I can say math, convert that to a fraction. And then it says 1 over 3. Well, great. That's also what I found. Now, of course, this isn't just useful for converting repeating decimals to fractions, because that would be really stupid. But you can actually figure out all sorts of cases when you're wanting to consider what is the sum of all of the terms in a geometric series. But it only works if a series converges. In other words, it only works if the absolute value of r is less than 1, then you can use this. So it's really important, because not all geometric sequences, in other words, not all lists of numbers here, it's even possible to find the sum of the first infinity number of terms. Remember, this example for, right here, the larger number of n you go, the farther you go, just the larger your sum gets. The sum just keeps getting larger as you get larger n values, so you can't really calculate this because it becomes infinity. But here, however, see how you're adding smaller and smaller numbers each time. When you do a series, remember, you're adding. So you're adding smaller and smaller pieces, which become infinitely small, and that means then you can essentially find the entire sum, the sum of the first infinity number of terms.